Welcome to video number 20 in the Using iTrain tutorial series. My name is Bob. Welcome back. In the previous two tutorials we went through the 5 steps in preparing a locomotive for use in iTrain. In this tutorial we see some additional information and go into some deeper detail on some of the steps. Now this information is not essential for using iTrain. We've added this tutorial for those that want to know a little bit more. If you can pick up anything from it, then that's great, but don't be concerned if none of it makes any sense. In step 1, there's nothing new to add. In step 2, we set values for CV3 acceleration and CV4 deceleration using this table here as a reference. We use a value of 0 or 1 for CV3 and CV4 if we have a non-sound decoder, and if we have a sound decoder we'd use values between 2 and 5 for CV3 and CV4. And you choose the value that best syncs the sound to the speed of your train. By setting CV3 and CV4 to 0, we effectively disable the decoder's inertia simulation, so that iTrain then controls the loco using its own inertia simulation, which we set up in step 4. Now it may be possible to use other values for CV3 and CV4 if you have reasons to do so, but our recommendation is to start with the values used in this table. Later, after you are successfully achieving proper control of your trains, you can then experiment with different values of CV3 and CV4. For instance, some sound decoders use sounds that are triggered by CV values. Some sound decoders may use the value of CV4 to trigger the brake sound when CV4 is above or below a certain threshold. That threshold may be higher than the CV4 value that we have set, so the sound may not trigger. But each decoder manufacturer is different, so you always need to consult your own particular decoder's documentation, and also the documentation provided by the creator of the sound project that has been installed. But remember, if you later change the value of CV4, you will also need to readjust the reaction delay. In step 3, we created the speed profile. Now throughout these tutorials you'll often hear me say the phrase 126 step decoder and 128 step decoder, which may be a little confusing, but they are both the same decoder. When you purchase a modern decoder, it will be described as a 128 step decoder, which is a bit of a misnomer. It should really be called 126 speed step mode for consistency, and I'll try and explain why. You can think of a 128 step decoder as having 128 different values from 0 to 127. 2 of those values have a fixed meaning. Value of 0 always means stop. Now stop means a normal stop including any inertia control, and the value of 1 means an emergency stop. So that means an immediate stop without any inertia, which leaves 126 values which are used as the speed steps. And from iTrain's point of view, these are the only values that it can change. And these are the locations where the 126 steps of our speed profile are stored. It can be a little confusing because when you look at a speed profile, the value that is always missing is always the value of 1 for emergency stop. If you look at this loco's speed profile, for example, you'll see that there are 127 steps listed here, 126 and 0. 0, the speed step 0, you'll notice you cannot change. If you double click on it, it can't be changed. That is the one value that is fixed. If we go to speed step 1 or speed step 2, you can see we can edit and change those values. Speed step 1 to 126. The value that is missing is that emergency stop value of 1, which is often confused with speed step 1. And that's the reason when you select the type of decoder here, the list does not show a 128 step decoder, because from iTrain's point of view there are only 126 steps available for it to change. The 126 plus option here is for BDB compatible decoders, bi-directional bus decoders. So I hope that clears up what the 128 versus 126 step means. They're both the same decoder. In step 4, we set up iTrain's own inertia simulation by setting values for step duration and step size. Now you may recall that we were aiming for a step delay of between 100 and 500 milliseconds ideally, and certainly not less than 100 milliseconds. And we were using a step size of 1 if we had a 14 step or a 28 step decoder, and a step size of 3 to 5 if we had a 126 step decoder. Now you may be wondering, how does iTrain's inertia simulation work, and why do we use different step sizes depending on the type of decoder? Well, within iTrain, speed changes requiring just a single step are executed almost immediately. But when the speed change requires multiple decoder step changes, such as when the train is decelerating from 100 kilometers per hour to 60 kilometers per hour, the intermediate steps are sent with a delay between each step, as specified by the step delay value. So it is the delaying of the step change commands that effectively produce the change in the deceleration and acceleration rates. Let's try to illustrate that graphically. Here you can see a typical speed profile graph as used in iTrain. We have speed in kilometers per hour on the vertical axis here, and we have the number of speed steps shown on the horizontal axis down here. And we can see that this loco is fitted with a 28-step decoder. On the left here we see iTrain's Inertia Simulation settings with the step delay and step size for both acceleration and braking. And for braking you can see that we've set a step delay of 200 milliseconds with a step size of 1. That means if we brake from the max speed, which is 170 kilometers per hour in this example, to a stop at 0, iTrain will transmit a series of single speed step commands with an interval of 200 milliseconds between each of them, like this. So the speed steps are decreasing down with a delay of 200 milliseconds between each of them. Now, for illustrative purposes, the time interval that you saw and heard there was not to scale, but you should get the idea. And the important thing was that each step was being used as the train decelerated. And a similar thing would happen if we decelerated from 100 kilometers an hour to 60 kilometers per hour. We have the same settings here, but you'll see this time the speed will decrease from 100 kilometers per hour down to 60 kilometers per hour with the same steps between. Now let's change the step delay. So this time we've got a step delay of 400 milliseconds and see what effect that has. So you see now each step is being played, if you like, but the interval between it is now 400 milliseconds. So effectively the train is now decelerating slower. So that's for a 28-step decoder. Now if we're using a 126-step decoder, it's better to not use each of the individual steps that are available, but to use a bigger step size instead. Now why is that? Well, without getting too technical, it's to do with how speed step commands are transmitted from iTrain and converted by the loco's decoder into a voltage that is applied to the loco's motor to control the speed. So that was a mouthful. Let's try and see what that actually means. So here we have a diagram of how iTrain transmits a speed step command. So here we see the PC running iTrain, and here we have our command station, and over here we have our track with our loco on it, and inside there is a decoder which is driving the motor. Now for all computer automation programs, including iTrain, the connection between your PC and the command station will typically be either a USB cable here or an Ethernet cable. USB cables are relatively slow at sending and receiving data here. Therefore, if a lot of data needs to be transmitted, there's potential here for a bottleneck. iTrain tries to reduce the potential for bottlenecks by using a larger step size so that the intermediate steps are not used and therefore less data is being sent. When a 126-step decoder is being used, iTrain will try to prevent those bottlenecks by using larger step sizes so that the intermediate steps are not used and therefore less data is being sent. So again, let's try and illustrate that. Here we have a speed profile of a loco fitted with a 128-step decoder. You can see by the notches down here that there's a lot more steps. In fact, there's between 4 to 5 times more steps than a 28-step decoder. We've got a 200 millisecond step delay and a step size of 1. So let's see what happens when we do the same deceleration from 100 to 60 here. You can see that the interval is the same between the steps, but there are a lot more steps that iTrain needs to transmit. Almost 5 times more steps. And so that's where there is a potential for causing a bottleneck through the USB cable. And the way to overcome that is by increasing the step size. So here we have a similar setup with a 200 millisecond step delay, but with a step size now of 4. And this is the effect that it has. So you can see that iTrain has jumped to every 4th step until it gets to the step before its desired step, and then it selects that desired step. So now iTrain only has to transmit roughly the same amount of data as when it is using a 28-step decoder. Now, the interesting thing about this is that it now doesn't mean that our 128-step decoders are suddenly starting to form like a 28-step decoder. And again, without getting too technical, the reason is due to how the speed steps are handled by the loco's decoder here, and the way that the decoder interpolates the steps in the 128 step mode. And we'll not go into the detail about that. We'll just appreciate the technical stuff that goes on below the surface. So that is where the 3 to 5 steps for a 126 step decoder comes from. It reduces the amount of data that iTrain needs to send without any perceptible difference in the smoothness of the trains. Okay, good. So the last point I want to quickly touch on again in step 4 is the feedback offsets. The feedback offsets should have been entered when you originally created the loco. So they're not strictly part of the tuning process for the loco, but you may want to check that they have been entered correctly and also the length of the loco. But what I want to add to this particular section is a note about users of third rails. If you have a third rail, then the feedback offset will be measured from the front of the buffer or the center of the couplings, whichever is sticking furthest out. So it would be from there back to wherever the first pickup shoe is located. So that is it for this tutorial. Again, that was just additional details that are not essential for you to know and understand in order to use and enjoy iTrain. And then after that we start the really exciting stuff, which is train routes and stations and actions and signals and all sorts of other goodies. Hope to see you in the next video. Take care.